So yeah, our first presenter is Joshua Langlois from Pennsylvania State University. He is here to talk about the vibrational behavior of Olympic barbells. Welcome.
Thank you for having me. As she said, I'm Joshua Langlois from Penn State. I worked on this with Dr. Daniel Russell, and this is understanding the vibrational behavior of Olympic barbells under realistic loads. So Olympic weightlifting is a very common sporting event. It consists of three movements: the snatch, the clean, and the jerk. And these movements are all performed on what's known as a barbell. So a barbell is a standard implement you'll see in any gym where you can load weights on it, pick it up, and use it to gain strength. So this barbell, when used, undergoes what's known as whip, or to us, flexural bending. So the actual bar moves due to the weight being put on it and the forces applied. So if you watch this video, you can actually see the bar bend as I go down, and I come back up and it recoils. This is the whip that I'm talking about. In Olympic weightlifting, Olympic weightlifters can actually time this whip. So when they dip down, the bar flexes, and they can actually feel it when it flexes back up and use that to accelerate the movement upward to increase the amount that they can lift. And this is what I'm interested in and what we're exploring here to understand what makes a good barbell. To understand this, we did an experiment called modal analysis. Modal analysis consists of understanding how something moves, something vibrates. So to perform modal analysis, we suspend the barbells from elastic bands, these resistance bands, to create what's known as a free boundary. That's just essentially the bar floating in space. The best we can approximate this is elastic bands. We then attach accelerometers to measure acceleration, and we do this at the end of the bar because there's no nodes at the end of the bar, so the bar will always move at the end in any vibrational mode pattern. So in any of the ways it flexes, the end will always move. We then take a small impact hammer, which measures force, and we tap across the bar at set locations, and then we can actually map out how this bar moves from that tapping and measuring the acceleration at the endpoints. For this experiment, we used 4 20-kilogram bars under one load, 50 kilograms on each end. We also did 2 barbells with and without the sleeves, so the sleeves are where the plates are loaded. And then we did 1 barbell under varying weights from 0 to 75 kilograms on each side. So first, we're looking at the first bending mode. This is the main whip that you saw in that first video. And this is comparing a bar with and without sleeves. So if we stop this and we look at these bending modes here, and what I mean by mode is the actual shape of the barbell while it's flexing, we can see that without sleeves, we get this standard free bar motion, which has a higher frequency than when we put the sleeves on. This is expected. We thought this would occur. When you add mass to the ends of a bar, it decreases the frequency, the rate of oscillation. And it also shifts the nodes. The nodes are the white spots on the screen in the bar plots, and that's where there's no movement at all. The bar is just stationary at those points. Looking at the second and third bending modes, so everything has multiple bending modes, multiple degrees of freedom. So that first mode is the one you saw most in the video, but the entire bending of the bar is actually what's known as a superposition of all of these modes. So it's a summation of these modes put together with some multiplication factor on each. So we can look at these other modes and we see the similar thing here. The one without the sleeves has higher frequencies, the one with the sleeves has lower frequencies. We can also look at this under varying loads, and this becomes very interesting because Olympic weightlifters vary a lot in size. You have 50 kilogram women all the way up to 130 kilogram men. So that's quite a difference in weight lifted. So the bar bending will vary a lot with load. And this is a plot on the x-axis. It's the total mass of the bar with the plates. On the y-axis, it's the frequency, the rate of oscillation. And then each of the different lines is a different mode, so a different shape. So the second and third modes shown here correlate to the orange and the yellow lines there, or the squares and the X's. So we can see for the first bending mode, shown in blue with the stars, the frequency decreases as load increases. This is typical of a bar and what we'd expect to see. Something surprising is that the second mode, shown in orange with the squares, decreases slightly and then actually increases at high loads. This happens because the bar becomes more fixed. So the actual wavelength in the bar is less. There's less bar movement, and it gets shorter due to the high mass partway, because the mass isn't exactly on the ends, it's slightly inside. So you get a shorter wavelength, and with a set wave speed, wavelength is inversely proportional to the rate of oscillation. So we get a higher frequency. This is something we didn't foresee happening, so it was very interesting. We also can compare multiple bars. So what we have here is 4 different bars and also some simulated results. The simulated results are shown in the solid lines, and the bars are shown in the dashed lines. And what we see is the bars at high frequencies, high mode numbers, don't seem to be very different. We get great correlation between the bars, but around mode 2, there's significant difference between bars. So at the lower frequency ranges, there's larger differences, so the barbell is likely to matter. And that's where we're at right now with this work. We know that the bar matters. We know that it changes shape with load, changes frequency with load. So now we're going to go forward and take data with real Olympic weightlifters so we can see how they use the whip exactly and how the bar matters for them. And we're also going to measure women's bars. So this study was all done on 20 kilogram barbells, which is the standard for men. Women use a 15 kilogram barbell, so it's going to be slightly different. We expect slightly different frequencies, slightly more bending under the same load, that type of thing. Any questions?
I can start with a question. Here, I'll grab the mic so people can hear. So it looks like that first image was maybe of you weightlifting. Is that what inspired this work?
Yes. So I compete in the sport of strongman, which has some element of Olympic weightlifting to it. There's always an overhead press event, which is the Olympic jerk. So yes, I was interested in seeing how that correlated. I also have a few friends that do Olympic-style weightlifting that compete at the national level, and they were telling me about how they use this whip, so I wanted to quantify it and understand how it works.
And when did you get started with this research? Is it relatively new?
Yeah, I started this the summer 2025, so it's been going on about a year now. It's not my main research, so it's been a side project, but I enjoy it quite a bit.
Yeah, very cool. Do we have any questions online or in the room?
All right, thank you so much for your presentation. Our first question from our live stream is from Anushay Bandari. Anushay asks, how large is this effect? You mentioned testing this on Olympic lifters. Would a casual lifter be able to tap into these differences?
Yeah, so for Olympic-style weightlifters, we expect the percent to be in, or the effect to be in the single percent range, which doesn't sound like a lot when you say it, but for elite sports, a single percent makes all the difference. For the casual weightlifter, it's unexpected. You can see a little bit here as I do this. I am not an expert Olympic weightlifter. I have a hard time timing the whip myself. It's very hard for me to feel it exactly. There's a similar thing with golfers. The best golfers in the world can actually feel how the golf club bends as they swing, and they can use that to change how the balls hit. So I don't expect casual lifters to be able to feel this or use it very well. It's just at the very elite level.
That makes sense. Our next question is from Avery Thompson. Avery asks, what are some of the most common barbell materials used in weightlifting, and how much do they vary in terms of mechanical properties? Yeah,
so that's a great question. Let me flip to this slide here. So most barbells are made of some sort of steel, often stainless steel, sometimes chrome coated, sometimes with a Cerakote material. But chrome and stainless steel are the high norms. The Young's modulus, so the stiffness of the bar varies quite a bit. We see that there in the second mode on this plot, how the frequencies vary. The bars are all the same mass, so the only thing that can really change that is the Young's modulus, because they're also the same length, same characteristics due to regulations in the Olympic sport. So materials vary quite a bit. We don't have a good feel for this because no bar manufacturers will tell you exactly how they make the bar. It's all proprietary. There's another thing that varies in the bar, and that's the coupling mechanism. So there's the shaft of the bar where you hold onto it, and then there's the sleeves where you load the plates, and there's a coupling between the shaft and the sleeve, and that seems to also make a difference in how the bar bends. The coupling mechanism varies between bushings, bearings, or bare steel, where bearings seem to have the best coupling, and that's what the most expensive barbells use.
Good to know. I feel like we could, I'm sure all the Olympic coaches know about this.
I'm sure they do, yeah.
I think that's it for our online questions. So if that's it, we're all good. Thank you so much.
All right, thank you.